Recording.
First of all, I want to welcome everybody to the May issue of the GemQuest. Our GemQuest today is GemQuest Samurai Garnets Gemological Update. And I just want to say we're in our seventh year of broadcasting, and we are actually seem to be going further and further around the world each time we broadcast. More and more people are finding out about us. So if you don't be afraid to share our invitations with others so they can also enjoy the free educational opportunities that we give people through GemQuest. And just a little bit of a heads up, next month, in the end of June, we're going to have a returning favorite. Uh, uh, Arya Akavan, who is one of the world's leading experts on synthetic gems, is going to be giving Synthetic Gems Part 2. And those of you who saw Part 1 will probably be very anxious to catch Part 2 because he's a very thorough and good presenter. And his information programs are absolutely jam-packed. So it's a great learning experience. And talking about learning experiences, we are very grateful that not only do we have Clemens Schwarzinger as our technological assistant and support in Linz University, but he's also going to be taking time from his day to present to us today. And Dr. Clemens Schwarzinger is a professor of chemistry at the Johannes Kepler University in Linz, Austria. His research focus in terms of gemology is using spectroscopy to investigate minerals and gemstones, their treatment, country of origin, fakes, synthetics, etc. This research project he's presenting today was awarded the AGA Gemological Research Grant 2025, and he subsequently presented it at the American Gem Association Conference in Tucson 2026 for the first and only time so far. So you are privileged to get the second exposure. So those who never made it all the way to Tucson will now be able to catch what they never got to see back then when those who attended were privileged to catch Dr. Schwarzinger's presentation. So with no further introduction, I'd like to thank you for attending and thank you for putting together this talk, Dr. Clemens, and we'll look forward to hearing what you have to say.
Well, thank you, Ray. So I hope we can all see the slides now. Just have to move something here. Oops. So, okay, so as Ray told you, this is a talk that I put together for the AGA, the Accredited Gemologists Association, and it's about green grossular garnets, or many of them can be also typed sorry, now I forgot the name, Tsamarites. What a good start into the talk. So, and as you may know, that these green grossular garnets can be found in several places around the world. They can be found in Afghanistan, in Antarctica, some in Madagascar, but the majority comes from two countries, and that's Kenya and Tanzania. And we were looking into how can we analyze these materials and what can we do to people who do not have a detailed or a well-equipped laboratory. So can we use, for example, simple and cheap instruments to get the same results like the big guys can play with? So now if you would try to move, yeah, here it is. So I have to start a little bit with the garnets. So garnet is one of the gemstones that can be found in pretty much every color of the rainbow. You can see the colors that you typically associate with garnets, the red ones, the purple ones, yellowish, the greenish, but also blue. Blue is a color that you rarely see in the garnets, but it can be found. But today we're talking about the grossulars. The grossulars can be from colorless to slightly yellow to a big range of greenish, pinkish, and even some reddish materials. Where does the name garnet come from? Well, first in antiquity, we had a term to call all of the red stones, and the term was carbuncle. So that was for garnets, red garnets, that was for sapphires, red sapphires or rubies, and that was also for spinels. But the name garnet, or in German it's more obvious, granat, comes from the Latin word granatum, which means pomegranate, grain or seed. And you can see here, it's an open pomegranate. This is a detailed picture of the seeds that it has, and this is a garnet specimen. So it's obviously very likely, and this is where the name comes from. Of course, being a chemist, I have to force you to learn a little bit about the chemical elements that are inside the garnets. And garnet is one of the supergroup of minerals. So they have a general formula that says X3, Y2, C3, Phi12. Yeah, who can live with this? More interesting is we have cations with two positive charges, and they sit in an eightfold coordination. Then we have cations with three positive charges sitting in a sixfold coordination. And then we have a fourfold coordination for M plus 4. And the phi in our cases is always an oxygen. Now, if we go to the garnet groups, then we end up that the C is silicon and we have the Se3O12, which all have in common. And then we have divalent and trivalent, so the plus 2 and plus 3 cations that make up all the different end members of the garnet group. The ones that are of most interest for us, for gemologists or for pretty stones, are listed in this table here. So we have the top formula here, and then we have the end members down here. So what does it mean, an end member? An end member is when you have just one X and one Y, and this is the problem in nature, you can mix them. So you have many, many mixtures in reality, and very rarely you have really the end member of a special group. So we can subdivide these into two groups, the pyrrole spits and eugrandites. Pyrrole spit, where does this strange name come from? From the individual names of the garnets that we have. We have the pyrope, the almandine, and the spessartine. And if you take the first letters, it's pyrrole sp, and then you have to add the ITE for being a mineral specimen. So the pyropes have magnesium and aluminum. The almandine, iron 2 plus, and aluminum, and spessartine has manganese and aluminum. So what they have in common is that the Y position here is in aluminum, and everything else can change. The second group is eugrandites. In eugrandites, we have the euvarovite, which is calcium and chromium, grossular, which we're going to talk about today, with calcium and aluminum, and andradite with calcium and iron. So in the eugrandites, we have the calcium as the bivalent cation as a common feature. And you see that the grossular is somehow a little bit special because it contains the calcium for the eugrandites, but also the aluminum that would allow him to fit it into the pyrrole spit group. So it's a little bit in between these. The name grossular comes from the gooseberries, or in Latin, ribes grossularia, and you can see that this is this nicely greenish color, and this is what many of the grossulars have. But grossulars can also have different colors. A pure grossular without any chromophore is colorless. Then you can have these raspberry garnets, which are grossulars colored by manganese. We have the hassonites with a cinnamon color, very famous from Canada, for example, from the Jeffrey mine. They have chromophores like iron typically. And then we have the tsavorite. Tsavorite are the greenish colored grossulars. And again, this is one of the big problems. It doesn't have a real definition. What is a tsavorite? What shade of green does it have? We don't know. Many people associate the darker green ones to be the tsavorites. Lighter green ones can be other names like mint garnets, Merilani mint garnets, or whatever. Being a scientist, I do not really judge. I just take all the greens and put them in the group of tsavorites, just to make things a little bit more easy. So, why did we start this project? Of course, we had a couple of nice green garnets in our collection, and at some point you start to play around and use UV torches. UV torch is something that everybody should have in their pockets because they help you so much. They give you references, they can put out fakes, treatments, many, many things can be seen under UV light. And our green grossular under UV light turned a bright orange. Wow, that's nice. So we have a fluorescence. However, that was not the only color that we have seen. We had another one, and that was just shining out in dark red. So this was puzzling us, and we said, okay, what can we do to investigate this? A little bit was known already. Some chromophores were known, but the question was, can we now use a simple UV torch and tell things apart? We don't know yet what we want to tell apart, but just to see how many different types of fluorescence can we see. And being a scientist, we just do not only look at the color that we see, the orange and red is nice, but describe red to another person. There's so many different types of red and shades of red. We all know that women can see many more red tones than men can because it's a physiological phenomenon. But as a scientist, you just record a spectra. So you see here we had the incident light, it was at 405 nanometers. So this is at the borderline between blue and UV light. And then the orange one had two bands that show up. We have one in around 700, 750 nanometers, and the other one just shy of 600 nanometers. Whereas in the red one, we just have the second band. So what is going on? Can we correlate it? And what can we make use of these data? So here you have a typical arrangement of grossular garnets you can find from East Africa. The almost colorless, slightly yellowish ones. The ones that are typically known as the type of Merillani mint garnet because very often they're found at the Merillani mine. And then you have the intermediate, the dark ones, and then the very dark ones. And now let's have a look how they behave under UV light. And you see they can turn orange, pink, red, or have no fluorescence at all. Intensity varies broadly. So there is quite a field of different reactions that we see under UV light. And this is one of the questions, can we use this to identify, for example, if a Merillani mint garnet comes from Merillani? Or isn't it the case that light garnets from Kenya would have the same reaction? Let's see. So what was our research plan? The plan was to use a couple of cheap equipments that we had in-house, like a UV spectrometer. You can have this for below 1,000 US dollars. Just recently, a colleague of mine obtained one last week for below 100 US dollars. So they can be really, really cheap and helpful. And we compare this to the machine that we have in our institute. So this is above 100,000 US dollars. And you see it's a little bit more complicated. So the UV spectra is about, well, 2 feet by 1 feet. And we have this extra cabinet where all the rays are running through and pointing at our gemstones. We can do polarized spectra. We can do locally address the points. So this is high end. We wanted to have the same with the photoluminescence spectroscopy. Again, we can use the same GL gem spectrometer. In this case, we use the laser. And this laser has a very narrow 405 nanometer line. And we use this one to get the photoluminescence of our gemstones. Again, price below 1,000 US dollar. Compared to this one, so this is in fact a Raman microscope, but the Raman microscope can also be used to measure the photoluminescence. So you have a couple of different lasers, you shoot with laser on your sample, and then you have a very detailed spectrum that can be collected. Of course, it comes at a cost, and the cost is above 150,000 US dollars here. And of course, the machine that I love most in my office, of course, it gives me most of the trouble because it's very sensitive. But laser ablation ICP-MS is the machine where you have just a trivial damage on a gemstone, speaking about some holes 50 microns in diameter and 2, 3, 4 microns in depth. And from this small ablation crater, we can get the entire chemical spectrum of the materials. Of course, 300,000 is something that you do not have at home. Or I do know one person who has it at home, but he is a multi-billionaire. So this is what you see. You have a gemstone, you point at the girdle. Here you see these three small spots. These are the ablation craters. And after shooting at this, if you position it on the girdle, you don't see anything face up. Even if you would, you repolish it without any nominal loss of the carat weight. So what do we need next? Samples. This is one of the problems that you have to get your samples and you have to get reliable samples. So you have to have somebody who collects the sample for you if you don't collect it yourself. I myself, unfortunately, was never able to go there, but it's on my list. Let's see. But we had people who were collecting material for us and people that were trustworthy. We know that we have here Mount Kilimanjaro, so this is the border between Kenya and Tanzania, and we have here the Merillani mines, very famous for the tanzanites, but they also produce good amounts of the tsavorite garnets, or of these Merillani mint green garnets. And another location with good quality material is Lemshuko here. And in Kenya, we have Voi and Mkuki. And in between these, we have here a nice little square. We have most of the mines that are mined for the tsavorite garnets in Kenya. So going into the detail of this map, you can see we have here pointed out with the location numbers a couple of mines. And these mines are all mines by the owned by Bruce Bridges and the Bridges family. And he was kind enough to share his material with us, and we will share the data with him. So you can see many, many mines. This is 11 mines just from him. We have very often material that's dubbed Voi. So Voi is up here, but all the digging is in these areas. And you see, this is a range of about, let's say, less than 50 kilometers. So even, I would say 20 kilometers, where most of these mines are. And sometimes, like here, this is the famous Scorpion mine. We have samples from two different tunnels, which are just a couple of meters apart from each other. So this was one of the very interesting things. Can we tell apart two tunnels from the same mine? Well, let's see if we can. So that means samples. What do we have? We have thousands of samples that we're screening. We have selected about 300 for UV spectroscopy for the high resolution spectra, about the same numbers for photoluminescence, for UV spectra with the cheap material, for the PL with the Raman system. We scanned 480, so close to 500 samples, and 230, because this is usually the limiting part. It takes most of the time. It is most expensive. 230 were analyzed by laser ablation, ICP mass spectrometry, and they were always analyzed in triplicate. That means we shoot at three different positions in the same stone to get a little bit of a variation across different sections. So we had cut stones from bright to dark. We had patches of rough, but not only those. So this is roughly what we had as samples. Yeah, and this, of course, is lots of work, and being a professor, you don't have the time, so we hire students to do this. Thank you for Florian Blasel from the beginning on to do all of these stuff for me. Let's start with UV spectroscopy. In UV spectroscopy, if you're not familiar with the technique, you have a lamp, and the lamp illuminates your stone, and then you record over the visible range where you have absorption. And here we have an absorption at 600 and one absorption at 400. Visible range would be between 400 and let's say 700, 750. So what we're seeing is where we have the lowest absorption, and this is 500, 520 nanometers. This is the green area. This is just three different samples from three different mines, and you see overall they look pretty much the same. There are differences, yes, but the major features are identical for those stones. If you go into more detail and compare them by saturation, so going from the almost colorless one to this Merilani mint to a nicely well saturated to a, I would say, a little bit oversaturated dark green, you can follow this pattern here. So the gray curve, that's this one here, has a small absorption band here, a continuum, but in the visible range, pretty much nothing. Then we go to the light green, and you see here's a small bump at 600, here's a small bump at 400, 450, still very bright. And then the same bands, the 600 and the 450, they increase. And what can already be seen here is the dark green one has a strong absorbance, and it doesn't show this valley here. So that means even in the UV, where this range is, we have a total absorbance. Okay, first test. Let's test our good spectrometer versus the cheap one. You see here on the left, this is what we get, high resolution spectra. We see one band at 605, a small side band at around 670, another one 425, and a 330 here in the deep UV range. What we have with the cheap one is, let's go from the right side to the left side, 605, which is identical with the other one. Then we have 447, which is shifted a little bit to the right. And then we see that the noise is getting bigger and bigger and bigger. So we can cover the visible range pretty well. The blue is, well, borderline, so we have a little bit of shift here. But what's the difference between 425 and 447? I mean, nothing for the naked eye. But we lose all of the intensity and the resolution here in the UV range. So this is the question, do we need it? And what is the reason for this? Well, it's easily explained. If you look at a modern spectrometer, it works like this, that you have a separation of your different wavelengths. So you just have your light source or light sources, there are more than one, and then you select one wavelength. And this wavelength now goes, for example, this is a two-ray spectrometers. It goes to a semi-permeable mirror where part of the beam goes through the gemstone and then to the detector, and part goes by another mirror into a reference detector. So we measure what would be the intensity if the light would not go through the gemstone versus the intensity when the light goes through the gemstone. And of course, if the gemstone absorbs something, then we have a difference. This is done for each and every wavelength, and it means we always have 100% and whatever the value is here. Now, if you compare this to the cheap spectrometer, then we have something that records all the wavelengths at the same time. This is fast, this is sensitive, but it comes at a cost because we have to illuminate everything with one light bulb. And the one light bulb that most people are using is a tungsten lamp. Tungsten lamp, here is the spectrum that you get from the tungsten lamp, has a strong intensity or a very intense at 700 nanometers, works nicely, let's say between 500 and 900. But if you look at the UV region here, it's almost no intensity. And that means if I don't have any light that is shining through my stone, of course, nothing can pass through the stone. And this is the problem why we have these bad spectra here at the UV range. We would have, you would have to find some way of mounting a second light bulb here that shines in the UV region to get more of a homogeneous distribution curve. Okay, so let's have a look at what can we do with the mines. Now, we know that UV spectrum may help us, but we know that if you look at the batch of material that comes from the same mine, it's not necessarily all the same color. There can be light stones, there can be dark stones, there can be anything in between. So how can we deal with this? Or does UVV still give us enough results or enough accuracy to separate between various, let's say, various mines? First thing that we did, we tried to correlate if we can use the UV or the UVV spans to simulate or to estimate the amount of various elements that are there. In order to use this technique, we first had to research what the elements are that we're looking at. And this is the chromium. The chromium is the 605 nanometer band. And this is vanadium, which has a band at 430. Problem is they mix up in some areas and you have vanadium also some bands here. So it's not easily to separate them just by using this one band. And another problem that you have in UVV spectroscopy, especially if you're using rough material, you do not get an absolute value. You always get a relative value, and that means the thicker your stone, the more absorption you have. This goes on a linear scale, but it's sometimes extremely hard to measure the distance between 2 points, and especially with cut gemstones, it's very hard because the light goes in a couple of different paths. It's not only going straight through the stone. So therefore, this is one thing that we have coped with by using relative values. So we just add up our peaks, take this as 100%, and then divide one or the other by this amount. So in this case, we were just using the relative height at the first approximation, and here the concentration of chromium, and you see that there's a trend. The higher the amount of chromium, the higher is the band that you see at 605 nanometer. Of course, it's rather broad, but it gives you at least an estimation. It's a definite proof that chromium is contributing to this 605 nanometer band. With the vanadium, it's a little bit more difficult. We see that we have values somewhere between 500 and almost 4,000 ppm weight. That means part per million. And we do see, some high values produce high areas in the 430 nanometer band. However, we have lots of points that do not really produce any band at all at the 430 nanometers. So this is one of the problems. This is, for example, a bad resolution of your spectrometer. This is definitely a limitation here. So with a cheap machine, no chance at all. And even for the good one, it's very hard because this is some phenomenon that we have seen. Uh, if the stones have too much vanadium, they become so dark that you don't see anything through. And even fluorescence is quenched by these elements. Okay, so next step would be look at the photoluminescence. Photoluminescence, we have here the stone in green in daylight and wonderful orange fluorescence when shown with the UV light. Here again, the spectra that we record, and this is 3 typical examples that we find. We can have stones that have just the 717 nanometer band, which is due to the chromium again. Then we have those stones that have a majority of these 490 nanometer bands, which is due to manganese and a little bit of the chromium. And then we have those that are mixtures in different ratios. We hardly find anyone that does not show at least a small chromium band, but we do have some that do not show any of the manganese band. First thing, make sure that you're measuring with the right system. What is easier, measuring the area of such a complicated peak or just the height? Well, height is much easier. Therefore, we're trying to correlate the area with the weight. And this is the nice correlation. You see most of them have very high values here. We dubbed this the luminescence value. And the luminescence value is the amount of the 760 nanometer band divided by the sum of both bands that we have. So it means if you have 100, then you just have, let's go back, then you have just this spectrum. And this one would be very low value. I would say this is this value here, down there. So this is a nice correlation, and this says, okay, we can use easy things, easy measurements, because integrating peaks that look like this is a mathematical problem that I don't want to bore you with at this point. So the first approach was use the intensity of the fluorescence and use the percentage of our luminescence value, which means a little bit manganese versus chromium. And you see we have a couple of mines here. We have differences. We see some distance, some difference. We see that a couple of those mines have very high intensities. The bigger the diameter of these red bulbs is, the more intense they are. Some are really, really tiny. Some do not show fluorescence at all. So let's see if we can work with this. If you use it in a table, then you see that the luminescence value for most of the stones is in the high area. Some show values that go down to 85%. So that still means its majority is caused by the chromium. If we look at 2 different mines, we have one that was, I got it from my good friend Steve Ulatovsky, that was mined in the Voi area. So we don't have the exact location for this one. And for example, we want to compare it to the Ericon mine. So we have here these 2.5% that we enlarged here. And you see that the deposit from Voi doesn't have any value in here, whereas the Ericon mine has a lowest value of 98.7, whatever. So if you just look at 2 mines, you can easily differentiate between them. If you have something like the CG1 mine that spreads across everything, you can of course not separate them from any of the other mines, except maybe from this Voi deposit. So first small positive result, I would say. Next thing that we wanted to check again was how is the correlation with the elements. So we had an abundance ratio, which was taking into account what do we see from the chemistry and from the luminescence spectrum. For example, if we take the chromium concentration divided by chromium, manganese, and vanadium, which are the chromophores that are responsible for the phosphorescence, or that we have seen that interact with the phosphorescence. So this abundance ratio for chromium versus the concentration of chromium, we see a trend. So the higher we go, the better it fits. Unfortunately, what we have very often is this 100% value. This means we don't have any of the other peaks contributing to this, and therefore you would have to exclude these values because they don't really give you too much information. On the other hand, we did the same with the manganese. Again, the same idea. Yeah, in this case, well, if you know what you're looking for, you can see a downward trend, but it's not as clear. I mean, this is also not really clear, but this one is even worse. You get a trend, yes, manganese is responsible for the 550 nanometers, and the chromium is definitely correlating with the 716 nanometer bands. So we're pretty sure that these two chromophores are the ones that give us most of the fluorescence that we see. If we look at the chromium, we get some correlation. If we look at the vanadium, however, it's very interesting that the higher the vanadium concentration becomes, the lower the fluorescence intensity is, which means that the more vanadium you have, the darker the stone is. You remember the band that absorbed completely in the UV range? The more you have of this element, the more likely you will see no fluorescence at all. So vanadium in our case is the luminescence quencher. This is something that is very well known in rubies, for example. In rubies, you have again the chromium, which gives you the red fluorescence. And if iron is present, iron quenches this and you don't have fluorescence. This can be used for separating, for example, a mogok ruby from a Thai ruby. Thai rubies have too much iron and they don't show the bright fluorescence. So this is the same here. In this case, we have chromium and manganese as the chromophores, and we have the vanadium, which gives us the green color, yes, but it disturbs the fluorescence that we are investigating. Yeah, then we had another instrument. This instrument was operated by my brother, who is at the University of Bayreuth. And in this case, we had the chance to use not only one single wavelength for enlightening our stones at 405 nanometers, but we could scan from 300 to 550 nanometers or even to 700 nanometers, so the whole range of slightly UV to visible light. And if you look at the 405 nanometer, that would be just cutting this three-dimensional plot here in two halves, and you would see flat, 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 and here's the chromium absorption. So the more greenish, reddish, yellowish spot is, this is pointing outwards as a peak. But what we realize in this one is we have a little bit of fluorescence here and here. And even if we go to around 700 nanometer, we see strong fluorescence of the chromium. If we have another sample, again, this is what we have here. This is the 600 or 590 nanometer band. So this one is the manganese related, and this one is the chromium related. So far, not too much new, but you see that there are other points shining up here. So we have another source of fluorescence that we find. And if we go through all the samples, you see, wow, there's something here at 400 that can be accelerated or can be excited at 300 nanometers or 360 nanometers. There's another one at the 600, there's another one at 500. Using different wavelengths, you can see different colors. And then we were just running through a little bit of software and let it check for ourselves what is the best wavelength that we use. And we decided we go through the 550 because we see still here the chromium, we see a little bit of the manganese, but we see a couple of additional bands as well. So this is what we see here. This is the typical medium green, and we have this spectrum. This is one of the brighter ones, and we have this strong manganese together with the other two. Well, with the naked eye, you can see the difference, but if you have 400, 500 samples, then they just overlap, and this is what they look like. So this is all the samples that we have and all the spectra that we got. Now, what we did start now is using machine learning algorithms, because if you have so many data, it's nice to look at them, but it's much nicer if you have somebody doing the work for you. And machine learning algorithm, or artificial intelligence, as it's also called, they look at the spectra, run through all these data points, and then they check which point should I use to get the best separation for a given problem. So in this case, the problem that we asked to solve was, is the garnet from Marilani or is it from somewhere else? So very simple, just verify if it's from one mine. So the truths are Marilani, you see very strong here at the 500 nanometer region, and the false one are not from Marilani. So the software picked out a couple of lines where it measured the intensity and then did a check, and it was possible to separate here basically the Marilani 100% from other things. What we have here is so-called cross-validation confusion matrix. What do we see here? We have a false and a true value. This is what we're asking from the software. And then we have either, okay, everything that is not Marilani is predicted as 100%, is measured as 100%. If we do prediction, then we have this class here. Again, there's nothing here in the wrong side. However, if we have Merillani samples, we used 15 here, then we have 5 that showed up as Merillani and 10 that did not show up as Merillani. So that means all the Merillani materials were 100% identified as Merillani material, and all of those that were predicted to be not from Merillani were also not from Merillani. We just had 5 samples that were predicted to be Merillani that were not Merillani, which is for the first test and for just a simple question, a rather good result. Well, of course, we had not just 2 questions, we had many, many questions. So you start to run all the mines, you start to run a couple of algorithms, and you see some work nicely, with some you have problems. For example, the MG mine that we had here, we had none of the spectra assigned here, whereas for the K mine, we had 100% wrong assignment. This is the 200% wrongs here, here's the 100% wrong, and none assigned here. After modifying the algorithm a little bit, don't ask me how this is done. This is the work of my dear brother. We got much better values. You see here 90%, 84%, 83%. So we're rather confident that we can separate many of the mines, but still you have some areas where you say, or you have to say, even as a lab, it's not conclusive. We cannot really tell you if it's from here or there. Now, let's use chemical data. So the data so far, we're just using the UV, the photoluminescence data that we obtained from the 450 nanometer excitation. Now with the laser ablation, I've shown you before, you have a laser, you shoot on your sample. We ablate material that goes into a plasma. The plasma is something like a sun, a small sun, that has a temperature of 10,000 Kelvin or degrees centigrade, doesn't make a difference here. So it rips everything apart and we just have atoms and ions there. And the ions go through the mass spectrometer and get that separated by their mass, which means which type of element it is, and then they're detected, which gives us the concentration. And therefore, we can map all these stones. Gives you huge data sheets. This one is where I just indicated my visual observation of the fluorescence that I was seeing. So red one, pinkish one, whatever color is orange. And here you have all the elements that we were measuring. Doesn't give you lots of ideas. If you go through it, well, you can do some easy tests like, let's sort everything by the concentration of chromium. Highest concentration of chromium on top, lowest concentration of chromium here in the bottom. And you see that all the reds and the pink ones show up here, whereas the oranges are with the lower chromium content. We did the same for the vanadium. You can't see this here in the colors, but no fluorescence, no fluorescence. The ones that are weakly fluorescing are here on top, whereas the strongly fluorescent one are more or less here with the lower concentration of the vanadium. Of course, you can try to just correlate the elements that you have with the locations that you have. So my master student did a nice job in measuring all the samples, and then he was, well, trying just to use vanadium and chromium concentrations to figure out if he can assign all the mines. I said it's simply not possible, but at least he came up with some trends. You see, there are a couple of groups, 1, 2, 3, and they go more or less in parallel lines. So there is a correlation between chromium and vanadium. Of course, it's not good enough to separate all the mines, but if you play around a little, you see that you can separate a couple of mines from the others. And for example, you have here the CW mine, you have the Ericon mine, and you have tunnel number 2 from the Scorpion mine. We had tunnel number 4 from the Scorpion mine as well. And this is here. So by just using all the elements, not just the 2, this is for all the elements, and some technique that's called principal component analysis, which automatically separates multidimensional data in 2-dimensional diagrams. This gives you a chance to separate one mine from the other, which are just a couple, well, 10 meters, 20 meters apart from each other, which is not too bad, I would say. And again, we did this with our artificial intelligence, and you see, you get these matrices. Here are the name of the mines, and here are the name of the mines. This is the true values, which means I have the alpha mine, 21 samples. I measured them, and all these 21 samples were assigned correctly as the alpha mine. That means 100% correct assignment. On the other side, there's one sample of another mine that is also assigned as the alpha mine. So that means, okay, we have 5% error here. Again, there's one problem that we have here and here in this axis, where we have these orange ones or nothing, where we have the problems with the model. What can you do? Of course, you can increase the number of data, or you can lower the level of your question, for example. So if you go just to, let's compare two mines, like the CG1 versus the unknown Steve mine. We just want to know if the mines that was labeled as void, so somewhere in the area, was the same as CG1. And this is the ideal case. It says 78 samples of the CG1 mine were assigned as CG1, and none of the others was assigned to this mine. As well as the other one, 30 assigned to the correct mine, and none of those to them. So we had 100% assignment that those two can never be mixed up again when using the technique that we have. If you increase the number, then of course you get a little bit more errors inside, but still, if you look here at the data, 98%, 70, 70, 96, 86 and 96%. So you get really good chances that you get the right answer for your question. Not too bad, I think. What also helps you is if you group them together, because you have seen a couple of mines behave similar. And therefore, we grouped them into three different groups. And with three different groups, we had, okay, the first group can be assigned perfectly as this group number one. We dubbed this AK. And then in the second approach, you go with the AK to the individual mines and then tell them apart there. So this is easy. The second group, which was the biggest one, we had something like 490 samples. 467 were correctly assigned, 17 were wrong, so this is 3.5%. And the fourth one was 250 samples, from which 227, so almost 90%, were correctly assigned. And here is the wrong assignment from other groups. So from the second group, 17 were assigned to the third group. And here from the third group, 27 were assigned to the other one. So still everything in the good 90s. We can at least assign these group, tell those apart, and then go into more detailed analysis further on. Yeah, this is the short story of a couple of years of work, still ongoing. What else do we have in mind for the future? What are the problems that we're facing? The problems that we're facing is that the quality of material that you're getting is not always the same. Like on the left side, we have called this little guy our stormtrooper. You can see here the eyes, the helmet, and so on. It is cracked, which is a problem for everything where you want to shine light through. It is grossular in most of the sample, but the eyes are made of quartz, and around the quartz, in between, is zoisite or tanzanite. This is nice. If you look with the microscope, you can see a nice blue eyeliner if you want to have. So this is a multi-element sample. If you shine your spot with the UV-vis analysis through here, perfect. If you go through here, you get completely different results, and you might not even realize it because it's just an optical absorption if you don't do the chemistry together. Or in this case, we did Raman mapping to find out which point was which. What we want to have is always clean samples, no inclusions at all, perfectly flat. Even better if you can polish them to a certain size so you can measure everything quantitatively. Unfortunately, if you have the gemstones, people don't really love it if you, say, I had to grind it down to 2 millimeters just to get the better data, and we know that it has come from that mine, but it's worthless now. So this is the problem that you have to deal with, and you have to figure out how to deal with these problems. And of course, also quality of samples is important, that you have to have reliable dealers and reliable sources where your material comes from. Well, I thought I couldn't leave you without talking a little bit about the situation and showing you a couple pictures. So getting tsavorite rough over the last couple of years has become more and more complicated. I was able to get one lot of these material, which you would dub Merilani mint. It has a little bit of a grayish touch, I would say, that sets it apart from the pure bright green of the Merulani, but this one comes from the Voi region, from Kenya, and it does show fluorescence. So fluorescence alone does not tell you that something is coming from the Merulani mine. You need to have the spectra, the complete spectra that, like I showed you at the beginning, to see where this really comes from. And you can cut nice stones here, more on the bright side. Well, I would say this one definitely qualifies for tsavorite. For this one, many people would say it's too light to be a tsavorite. Getting real good dark material is a thing that is close to impossible if you don't have your mine. If you own the mines, of course, you get some material. Or if you're not down at the market, so in the second-hand market, like we have a broker in between, it's almost impossible to get anything of good size. Good size means I'm talking about 5 carats upwards in the rough. So this year I was able to get one stone after a couple of days of negotiation, just because I said, okay, this is for a ring for my wife for the 25th anniversary that we're having this year. And this ended up at just shy of 2.5 carats. Something like this is basically not available at the open market. And I'm looking for material like this for many, many years now. It's getting harder and harder to find good tsavorits. Don't know if everybody else has other opinions. I would be glad to hear about this. But my experience, if you want to have some saturated material that is above a gram in size, then either you have to sell your liver or it's not possible. So, of course, this project has too much data to be done alone. I already told you that I had a master student, Florian Blasel, who was helping me. Christina Demchisinova was doing her bachelor thesis. My dear brother is a professor at the University of Bayreuth, and he also abused 2 students, Sophie Krauschke and Alessandro Nicolas Burger, who were acquiring the data. And of course, I'm extremely grateful to Bruce Bridges, who was giving us many, many samples, way more than 100 samples with detailed locations. And also he was allowing us to share the locations of the mines so that I could share those with you. And as a final slide, I can only say, it's not easy being green. And this, for example, is one of these nice materials that has been carved by Michael Perster, photo here by Elijah Nix. This is daylight and this is under UV light. And this is what started our project, and this is with how I would like to end with this project. So thank you everybody for listening. And if you have any questions, just open your mics and let me know.
Um, may I ask a question?
Of course.
Um, First of all, thank you so much. That was great. I learned a lot. I really appreciate the time that you put, and also Ray, thank you. Do you find, I might have missed this, do you find horsetail inclusions in these garnets? Like
horsetails? No. I mean, I don't want to say no, definitely, because I have found one garnet that had horsetail like inclusion. It was published in the Journal of Gemology 2 or 3 years ago, but it was not green. It was more of a cinnamon orange color that had a grossular composite on it. As I told you, it's always mixed garnet, but the classical horsetails, a typical sign of androdite garnets that can be found in Iran, Russia, of course, Italy, couple of places, Canada as well does show horsetails. And this is very often due to the location where they grow in, due to the geology. So they are growing in asbestos deposits.
I might have a question or two if nobody else does. Okay.
Yep, sure.
All right, thank you. Well, first of all, I'm just kind of curious if is there a huge difference between UV visible spectroscopy that you're doing versus Raman? Or is the main difference between them one has laser ablation and the other one does not? I'm curious.
No, that's now a couple of techniques that you're mixing up. So
Okay.
the UVV spectroscopy is a spectrometer that just records the absorption in the visible range, or sometimes in the infrared range, or in the UV range.
Okay.
So if you do the classic UV vis, then you have a light bulb in the visible range. the photoluminescence is now if you use a typically UV laser to get more power into the system to excite more of the electrons, and then you get the same spectrum. Raman can be used to do this photoluminescence. We did not talk about Raman here. So the classical Raman technology would be used to identify the material as a grossular garnet, for example.
Gotcha.
And the laser ablation ICPs, again, a different machine. Here you shoot with a laser of much more power. So you really shoot holes, whereas in the photoluminescence in Raman and FDIR, you just have a laser with very low power that doesn't harm your crystals. With the laser ablation, you really shoot something out of the material, and from this material that's ablated there, you get the chemical data and the chemical profile.
Got it. Thank you very much. I appreciate that. I do have one other question regarding the graphs that you were showing. One of the earlier graphs you were showing, it got really busy, on the downstroke there.
Yeah.
And I'm curious, whether you have the ability for like multiple passes of the beam or of the test. Would that refine that any, or does that even make any sense?
To a certain extent, yes. It's always the longer your measurement time is, the more you average your data. So therefore, your noise is becoming smaller and smaller. But it doesn't help you with the problem that there's so low light intensity in this region from the tungsten bulb. So better than measuring many, many, many hours in this case would be that you have a second light bulb that has a better emission in the UV, like something like a mercury lamp.
Okay.
The problem is that the mercury lamp will harm your eyes. So you have to make a special cabinet around everything. And then, yeah, that could help.
Thanks very much. I appreciate it.
You're welcome.
Clemens, I have a question. You asked at the start, you said at the start that there are also blue garnets. And I haven't heard of this until today. So please tell me more about it.
Okay, blue garnets are, for a long time, people said there are no blue garnets.
Yes.
So blue garnets have been found in Bekili in Madagascar, in Kamtonga in Kenya, and they typically have a mixed a mixed chemistry, different elements where pyrope is very strongly present. And they have a chromophore, mostly vanadium, that gives you a band somewhere in the middle of the visible range. Now it depends of your light source. You can have either one that's more in the daylight spectrum or that's more in the candlelight spectrum. And that would interfere with the spectrum either on the one side or on the other side. And therefore, most of these blue garnets are color shift garnets as well. So you have them blue to green or blue to red. What you have now is some cases where the blue is dominating in the daylight and you get really nice blue garnets. I do have one here, but I think you can't see the color most likely if I hold it up.
Oh, it's nearly black.
Yeah, it's nearly black. That's the problem because this one is also huge. So if you see a blue garnet that is above 1 carat, jump on it, try to get it. It's worth it. This one I just showed you is above 5 carat.
Wow.
At least for me, it's the largest that I have ever seen. But of course, the saturation becomes much better. I had one 2 years ago that was around 1.52 carats, something like this. That was the one in the photo that really showed nicely the blue color. And also it changed color depending on the light source that you have from blue to green to gray and what was the one, the reddish pink.
Do you have an idea about the carat price for such a cut stone? A nice color.
If it's good quality, it's 1,500 upwards.
Okay, thank you.
So not the typical garnet prices that you're looking for.
Okay.
And good luck trying to find a blue.
Yeah.
They're very hard to get. I have people who for whom garnet is their birthstone, but they don't like the color, and their favorite color is blue. And I'm saying, well, it's possible, but it's going to take a year or more to try and find a good one.
So we have here a question from Nolan. So if we can tell the two scorpion mines apart, would that imply the stones were formed or deposited in two separate events? Oh yeah, you nailed it. The only thing that we so far cannot tell if a mine produces the same results over time, because we just have mostly one pocket from each mine. So it can also be that two pockets behave completely different because they were formed in different geological events. In the case of these two tunnels, definitely yes, that was the case. Uh, but again, we would need much more samples and many more samples from the same mine, from the same tunnel, but from different pockets. This is the weak spot that we still have, that we, yeah, despite having more than 1,000 samples, we still do not have enough.
Yeah, I imagine um, well, fluid flows can change their chemistry over time as well, right?
Yeah, of course, we know it, especially from tourmalines, that they are multicolor, but also garnets can be multicolor, and you have a change in chemistry through the crystal. We had samples
Right.
of demantoid that started out in this red in the center and then went to a intense green, pale green, intense green back. So this was correlation. The first one was titanium, then we had chromium in between, some vanadium and so on, other elements. But still, with our technique, we were able to separate even this multi-zoned crystal in its right location. The question there was demantoid garnets from Madagascar, Namibia, or Russia, for example.
Yeah, and the word I was looking for was hydrothermal.
Uh-huh. Yeah, I mean, all the events, they change their chemistry over time. Crystallization always starts with one pure component, and if the pure component gets less and less abundant, other material comes in, and this is often where the color comes from.
Very cool.
Well, have any more questions? If not, I want to give my absolute thanks to Dr. Schwarzinger for his work and his time, and for sharing with us today the very technical aspects of his study, which not all of us can use, unfortunately, because of the level of equipment. But I think the light at the end of the tunnel was that one of the outcomes was that you can use simple technologies in the way of a black light or a fluorescent light to actually make determinations that don't require much more exotic equipment like he's been using. So I think that's a good thing, and I'm hoping that from this will come some suggestions for easy identification and location using just a black light. I don't know if that's possible, Clemens, but it certainly seemed like that was what you were hinting at.
It's always, there will be cases where it is easy to separate them, and there will be cases where we run into problems. So don't forget the inclusions. We have the inclusions as well. Uh, Use everything that you have, whatever kind of filters that you have. But the black light is one of the things that everybody should just wear all of the time. Even if you go into a bar, use the UV light to shine on your drinks, and many of them will fluoresce. That gives you at least a nice party trick.
I
uh,
do have one more question for you regarding all this, if you don't mind.
Yeah.
Just inevitably, the information that you guys are gathering, will it inevitably become a public resource, or only through professional associations or anything like that? Or is that strictly for your own study, your own labs?
Well, working at the university, one of our missions is always to publish things. And if we publish things, it is more or less freely available. Depends on the journals. Some journals, they give the papers for free. For some, you have to pay some 40 to 70 US dollars per paper. But in general, we try to share the information. We're not a professional lab. I know that professional labs will sometimes keep those databases strictly confidential because this is their working model. If you
Mm.
want to be better than the competitor, then you have to have something that he doesn't have. But as a university, of course, we like to share everything. And it is an ongoing work, so we're not yet at the stage where we dare to publish the results. We just want to have everything together. So maybe another half year, maybe a year, depending on how much workload we have. But then we would like to publish this as well.
Thank you.
There's another question there, by the way, Clemens. It says, is there any place we can find the colored lists you show in your presentation?
The colored lists. Yeah, this colored list will again be in this paper. So far, I show them in the presentations, but you cannot read them, of course. If you have any specific interest, just send me an email and I can send you the copies, because it's not easy to share these data as well. You have to have the right software. You have to have the capability to look all these big data. But if somebody has a special interest in it, I'm always willing to share.
And in addition, of course, this program will be available online once it's been stored at
Yes.
the university. So that's the other aspect as well. So thank you very much, Dr. Schwarzinger. We really appreciate your offerings and your information. It was very well done and made so that most people could understand exactly what you're talking about. So we'll look forward to the next program, everybody, where we're going to have in June next month, we're going to have Ari Akavan talking about more about synthetic gems. And this is actually the other side of the coin for most of us. I personally try and keep my practice in making jewelry to natural stones, but the synthetic stones are creeping in more and more. So I think it's good to have that information. And I'm hoping you will attend, and you'll pass along that information so that more people can benefit from our programming. And with that, I want to thank everybody for coming and joining us today. Thank you for your contributions, Dr. Schwarzinger. And thank you. Oh, there was one lady who was going to show us some slides. I don't see. Are you there? Are you going to show us some of your trip to the mine? I don't know if she's there. Maybe not. Okay. Well, thanks everybody, and we'll look forward to seeing you next month.
Thanks, Ray and Clemens.
Thank you and goodbye, everybody.
Appreciate you stepping into the front.